Hello everyone. Today we're going to keep working with graph sketching, and we're going to be using the same vocabulary that we've been working with the last couple of days. The difference today is now instead of getting all of this information about our function from a graph, we're going to be getting the same information, but now what we're given is the equation of the function. So we're not just picking this information off a graph, but we're using the function to figure out the behavior of our graph. So, like I said, the vocabulary is going to be the same. We're just going to do a little different process to find out where all these things are happening. So again, the first thing we're going to talk about are the critical points. And just like we said the other day, the critical points are where the derivative is either equal to 0 or is undefined. So if you'll think back, when we were doing this with a graph, we were looking for places on the graph where we had either horizontal tangents, that's where y prime was equal to 0, or we were looking for any cusps, corners, vertical tangents, or discontinuities. So now we don't have a graph, but we have a function. But we know easily enough how to find where y prime equals 0. Since this is a polynomial, there's nowhere it's undefined, so we don't have to worry about that. So we're just going to find our derivative. And so that's negative 4x cubed plus 4x. And we're going to set that equal to 0. And now we can solve to see where that happens. So I'm going to factor out a negative 4x. So I get x squared minus 1 is equal to 0. So I know my critical points are at negative 1, 0, and 1. Okay, so those are my critical points. So now we want to look for our maximum and minimum values. So just to review, our maximum values, those are going to be the high points on our graph. Or we called them our peaks before. And when we're talking about our absolute maximum, that's the highest point anywhere on the graph. And since now we don't actually have a graph to look at, what we're going to have to do is compare the values of the function at these points and determine the highest one. So we're going to determine value of our original function. So determine the value of the function at max values and we're going to take the highest one. And in a little bit we'll see, well, how do we do this given a function? Okay, then we had talked about minima, right? And we know those are the low points on our graph, or our valleys. And our absolute minimums were the lowest point anywhere. Right, and so I'm going to make a note here again. We're going to compare the values of our function f of x at our minimum values of x. And we'll take the lowest one. Now, at this point, it seems a little tricky to determine how we're going to find these maximum minimum values just by knowing these critical points. And so I'm actually going to move down and look at increasing and decreasing and then revisit our max and min values. So when we talked about increasing and decreasing, and let's see, I'll switch colors here. We said increasing is where y prime is greater than or equal to 0. Right? On a graph, we know that's where we're going uphill. And we said that for increasing and decreasing, we're always working with closed intervals. And so then for decreasing, that was where our derivative is less than or equal to 0. It's where our graph is going downhill. And again, we're always working with closed intervals here. So let's use our critical points to now figure out where we're increasing or decreasing. And to do that, we're going to build a table just like we did when we were looking at the graph of a function. So I'm going to use the critical points that I found above, and we said those were x equals -1, 0, and 1. And I'm going to build my table. Now, I know this domain of this function is from -infinity to infinity. So I'm going to look at my graph of y prime, or my equation, excuse me. And so I know at this endpoint I have -infinity. Then I'm going to put in my critical points. So I have -1, I have 0, and 1. And then at this endpoint I have positive infinity. So now let's see what the sign of y prime is. And again, that's going to help us figure out where we're increasing and decreasing. So if I look at, let's pick something here, say -2. And I'm going to look back up here at my factored form. If I plug in a -2, this is going to be positive. A -2 squared is going to be a positive 4, -1 is going to be a positive. So I know on this interval, y prime is positive. So my graph is going uphill. So I'm going to make a note here for increasing. I'm increasing on -infinity to -1. And then I try something between 0 and -1. So I'll plug in -1/2. Again, now negative times a negative gives me a positive. But -1/2 squared is a 1/4 -1, and that's going to be negative. So I know on this interval, my derivative is negative. So I'm decreasing. So I'm decreasing from -1 to 0. And I'm going to test all my intervals. Oh, I'm sorry, you can't see this. I'm going to test all these intervals in the same way. And I'll zoom out so we can see our factored form above. So now I'm going to test a point between 0 and 1, so I can pick +1/2. So up top, a +1/2 is going to make this figure, or this factor, excuse me, negative. If I plug in negative or a +1/2 here, I also get a negative. So I am going to have a positive derivative over this interval. So increasing, I'm also increasing from 0 to 1. And then last but not least, I'm going to pick a point greater than 1. I'll use a +2. So again, if I plug that into my derivative, my first term is going to be negative. My second is going to be positive, so that in that interval, I have a negative derivative, which means I'm going downhill there. So I'm decreasing from 1 to infinity. So now we know we're increasing or decreasing, and this is really the key to determining where our max and min values are. So if I think about what this function means, or what this information means, what I can see is that my function, remember this information about y prime is giving me information about the function. It's telling me that it starts by increasing, then it decreases, then increases, and then decreases again. So I can start to put together a sketch of what this function looks like. So that tells me that I have maximum values wherever my derivative changes from positive to negative. We see over here again, I change from positive to negative, and that's a max value. So I want to add that up here when we talked about maxima. Those are going to occur where y prime changes from positive to negative, right? They could also occur at endpoints. So for our example here, and I'm just going to add this down here because it's using this table. Let's see if I can zoom in here. I know that my max values occur at x equals -1, as I change from positive to negative, or increasing to decreasing, and it occurs at x equals 1. So now the question becomes, which of those then, and I'm going to zoom in a bit here, which of them is going to give me an absolute maximum value? So let's see if I can keep this here. So my absolute max, we said we need to determine the value of the function at the max values and take the highest values. So I'm going to look up here. I said a max occurs at -1. So what I'm going to do is take that -1 and plug it into my original function. So if I plug that in, -1 to the 4th is a +1. So I have -1 plus 2 times -1 squared is 1. So -1 plus 2 is going to give me a +1 for that value. And now I need to compare that to the value if I plug in 1. And you can tell pretty quickly I'm going to get -1 plus 2, which is also 1. So those are also both my absolute max. So I have an absolute max also occurs at x equals -1 and 1. They kind of tie for that absolute max value. Now, on the other hand, my minimum values are going to occur where my derivative changes from negative to positive. So my function changes from decreasing to increasing. So I'm going to add that here. They occur where y prime changes from negative to positive. So where my function changes from decreasing to increasing. And again, these can also occur at endpoints. So looking at my graph, I have minimum value. Let's see if I can fit this. That occurs at x equals 0 because I change from decreasing to increasing. So the last thing I have to figure out is where, if any, I have an absolute minimum value. But now, since this graph is coming up from -infinity, it reaches a low point, but then it goes back down to -infinity, I can never pinpoint the absolute lowest value of that function. So we would say for our absolute min, in this case, there is none. We can't peg down the absolute lowest value of that function. So that's how we get information in our maximum, minimum values and intervals of increase and decrease. So now we're going to look at concavity, which we know involves the second derivative of our function. So here we go. I'm going to scoop up my pile of pens here. Again, we have the same function here. So we know concavity deals with the second derivative. So I'm going to go ahead here. I'm going to use blue. We had our first derivative was -4x cubed plus 4x. And so my second derivative is going to be -12x squared plus 4. And again, I want to find where my second derivative is either equal to 0 or undefined. So I'm going to factor out a -4. So I get 3x squared plus 1 is equal to 0. So now I'm not going to get a super nice number, but that's okay. Oh, since I factored a negative, this is going to be a minus. Sorry about that. So now I get 3x squared is equal to 1. X squared is 1/3. And so x is positive or negative square root of 1/3. Again, not a nice, easy number to work with, but we can still deal with it. So, for concavity, if you think back, we said we're concave up wherever our second derivative is greater than 0. And we always work with open intervals when we're talking about concavity. And remember, we said if it's concave up, it opens up like a cup. We're concave down wherever y double prime is less than 0. Again, still open intervals. Let's make sure. No, that's not a great color, but you can read it. It's open intervals. And then we said it opens down like a frown. And so then our points of inflection are points where y double prime equals 0 or it's undefined, and the concavity actually changes. So until we make our table, all that we can say are that these are potential points of inflection. We don't know that they're actually points of inflection until we make our table. So let's go ahead and do that, and I know I'm a little pressed for space here, but we'll do our best. So now we're testing y double prime. Again, I know I go to negative infinity at this end, and then I'm going to put in my points of inflection, or my possible. I've got negative root 1/3, and then I'll have a positive root of 1/3, and then I go to infinity. And we build our table just like we did when we were looking at intervals of increasing and decreasing. So now I'm going to check out points. So into my second derivative here, I'm going to plug in a point between negative infinity and negative root 1/3, so I'll pick negative 2. So if I plug in a negative 2 into here, I'm going to get 3 times 4 is 12 minus 1. I'll have a positive times a negative. So I know that's going to be negative. So I'm going to have concave down behavior. In between these two values, I'll pick 0. So if I plug in 0, I get a negative inside the parentheses times a negative is going to give me a positive. So I'll be concave up. And then in my last interval, I'll take, say, a positive 2. And again, if I take a positive 2, I'm going to be positive inside the parentheses and negative out. So I'm going to be negative over that interval. So I'm concave down again. So just to summarize this portion, I'm going to be concave down from negative infinity to negative square root of 1/3, and also from, sorry about squeezing this in here on you, square root of 1/3 to infinity, and we'll be concave up in between those values. So that tells me I do have 2 points of inflection. These actually are my points of inflection because at both of those points, my concavity changed sign. So we will do, in the interest of time, we'll do the next example together in class tomorrow to get you started before you guys do some station practice on your own. So that's all we'll do for now, and we'll do this example tomorrow.